When we think of machine learning, many of us envision robots, either as helpful companions or as threats from a sci-fi movie. But the reality is far more practical and has been part of our lives for decades. Take optical character recognition, for instance. It's been transforming how we digitize text for years. However, it was the spam filter in the 1990s that truly brought machine learning into the mainstream. This technology learned to identify unwanted emails so effectively that we rarely have to mark anything as spam anymore. Today, machine learning is embedded in countless applications, enhancing our daily experiences, from personalized recommendations on streaming services to the accuracy of voice search. It's not just about futuristic fantasies, it's about real-world improvements that make our lives easier and more efficient. When I think about machine learning, I picture a world where algorithms are quietly transforming our daily lives. It's fascinating to realize that this technology isn't just a sci-fi dream. It's been around for decades. Take optical character recognition, for instance, an early application that changed how we digitize text. But the real game changer, the spam filter. Back in the 1990s, it emerged as a simple yet powerful tool, learning to identify unwanted emails so effectively that we rarely have to flag anything ourselves anymore. Fast forward to today, and machine learning is everywhere, enhancing our experiences with smarter recommendations, voice search, and even personalized content. It's like having a digital assistant that learns and adapts, making our lives easier without us even realizing it. This is just the beginning of a landscape that's evolving every day, quietly shaping the way we interact with technology. Machine learning begins with the idea that machines can learn from data, but where does it end? It's not just about downloading vast amounts of information like a copy of Wikipedia. It's about extracting patterns and making predictions. When we talk about machine learning, we dive into two main regions: supervised learning, where we guide the machine with labeled data, and unsupervised learning, where it discovers patterns on its own. We also have online versus batch learning. One learns continuously, while the other processes data in chunks. Then there's instance-based versus model-based learning, where some systems memorize examples and others build a general model. Navigating a typical machine learning project involves understanding the workflow, tackling challenges like overfitting, and fine-tuning our models for optimal performance. It's a fascinating journey through data and algorithms, where clarity is key. So let's unravel these concepts and see how they shape the future of technology. Machine learning is fascinating because it's all about teaching computers to learn from data, almost like how we learn from experience. Imagine a spam filter. It analyzes countless emails, identifying patterns in what makes an email spam or not. This process is called training, where the filter uses examples, known as the training set, to improve its accuracy over time. When we talk about a computer learning, we mean it gets better at a specific task, like flagging spam, based on its experiences. The performance measure, often accuracy, tells us how well it's doing. But here's the kicker. Simply downloading a massive database like Wikipedia doesn't make a computer smarter. It's the ability to learn and adapt from that data that defines machine learning. It's not just about having data, it's about transforming that data into knowledge and action. Imagine trying to build a spam filter using traditional programming. You'd start by identifying common spam traits, words like free or credit card. Then you'd write complex rules to flag emails based on those patterns. Sounds straightforward, right? But as spammers adapt, your filter becomes a never-ending list of rules to maintain. Now let's flip the script with machine learning. Instead of manually coding every rule, the filter learns from data. It analyzes patterns in spam and non-spam emails, automatically identifying new tricks spammers use, like switching "for you" to "for you." This means your spam filter evolves on its own, staying one step ahead without constant updates. It's shorter, easier to manage, and way more accurate. In a world where spammers are always innovating, wouldn't you want a solution that keeps up effortlessly? That's the power of machine learning. Machine learning excels in tackling problems that are too intricate for traditional methods or lack a clear algorithm. Take speech recognition, for example. Imagine trying to create a program that distinguishes between 1 and 2. You might think to measure high-pitched sounds, but that approach falls short when faced with thousands of words, diverse speakers, and noisy environments. Instead, the magic of machine learning comes into play. By feeding algorithms countless examples, they learn to identify patterns and nuances in speech. Moreover, ML isn't just about automation, it can enhance our understanding too. Consider a spam filter. Once trained, it reveals the words and phrases that signal spam, often uncovering surprising insights. This ability to learn and adapt makes machine learning a powerful tool, transforming how we interact with technology and each other. Machine learning is revolutionizing how we tackle complex problems. Imagine sifting through mountains of data. Traditional methods often fall short, requiring endless fine-tuning and cumbersome rules. But with machine learning, one algorithm can streamline processes and outperform conventional approaches. It's like having a smart assistant that learns and adapts in real time. In fluctuating environments, these systems thrive, continuously evolving as new data emerges. They uncover hidden patterns and correlations that we might overlook, providing insights that drive better decision-making. Whether it's predicting trends or solving intricate issues, machine learning is not just a tool, it's a game-changer in understanding the complexities of our world. Imagine a production line where machines analyze images of products in real time, classifying them with incredible accuracy. This is the power of image classification, often achieved through convolutional neural networks, or CNNs. Now, shift your focus to the medical field, where detecting tumors in brain scans is a matter of life and death. Here, semantic segmentation comes into play, classifying each pixel to pinpoint the exact location and shape of tumors, again utilizing CNNs. And then there's the world of news, where automatically classifying articles is essential for keeping us informed. This task falls under natural language processing, specifically text classification, and can be tackled using advanced techniques like recurrent neural networks, CNNs, or even transformers. Each of these applications showcases the versatility and impact of machine learning in our daily lives. Automatically flagging offensive comments on discussion forums is a game changer for online communities. By leveraging NLP tools, we can classify text and ensure a safer environment for users. Creating chatbots or personal assistants takes it a step further, integrating natural language understanding to interact seamlessly with users. On the business side, forecasting revenue involves regression models. Think linear regression or even advanced neural networks to predict future performance based on past metrics. Voice command recognition transforms apps into intuitive tools, utilizing RNNs or transformers to process complex audio sequences. Detecting credit card fraud is another critical application of anomaly detection, safeguarding users from financial threats. Lastly, segmenting clients through clustering allows businesses to tailor marketing strategies, ensuring each customer feels valued. Each of these applications showcases the incredible potential of AI and machine learning in our daily lives. Imagine navigating a complex, high-dimensional dataset. It's like trying to find your way through a dense forest. Data visualization techniques, particularly dimensionality reduction, help us cut through the noise, transforming that chaos into clear, insightful diagrams. Now consider a recommender system. By analyzing past purchases, we can train an artificial neural network to predict what a client might buy next, tailoring suggestions that feel almost intuitive. Then there's the realm of gaming, where building an intelligent bot often involves reinforcement learning. These bots learn to make decisions that maximize rewards, much like how AlphaGo mastered the game of Go by outsmarting human champions. The breadth of machine learning is astounding, tackling everything from data visualization to personalized recommendations and intelligent gaming agents, showcasing the incredible potential of technology in our lives. Machine learning systems can be fascinatingly diverse, and understanding their types helps us appreciate their capabilities. First, we have supervised learning, where models are trained on labeled data, learning from examples. Then there's unsupervised learning, which dives into the unknown, identifying patterns without any labels. Semi-supervised learning combines both, using a small amount of labeled data alongside a larger pool of unlabeled data, striking a balance between the two. Next, we explore reinforcement learning, where agents learn through trial and error, receiving feedback from their environment. Think of it as a game where every action leads to a reward or a penalty. Now, let's consider how these systems learn. Online learning allows models to adapt in real time, continuously updating as new data arrives, while batch learning processes data in chunks, refining the model only after a full dataset is available. Finally, we differentiate between instance-based and model-based learning. Instance-based learning compares new data points to known examples, while model-based learning builds a predictive model, much like a scientist forming hypotheses based on observed data. By combining these criteria, we can categorize machine learning systems in a way that reveals their unique strengths and applications. Supervised learning is a fascinating area of machine learning where we train algorithms using labeled data. Imagine teaching a spam filter. It learns from countless emails marked as spam or ham, allowing it to classify new messages accurately. This process is called classification. Now let's talk about regression, where we predict numeric values like a car's price based on features such as mileage, age, and brand. Here, we provide the algorithm with examples of cars, complete with their features and actual prices. In machine learning, the term attribute refers to a specific data type like mileage, while a feature encompasses both the attribute and its value, such as mileage equals 15,000. Interestingly, some algorithms can switch roles. Logistic regression, for instance, is primarily used for classification, but can also output probabilities, like a 20% chance of an email being spam. This versatility makes supervised learning a powerful tool in the data-driven world we live in. Supervised learning algorithms are the backbone of predictive modeling. Take K, nearest neighbors, for instance. It classifies data points based on their proximity to others. Then there's linear regression, which helps us understand relationships between variables by fitting a line to our data. Logistic regression, on the other hand, is perfect for binary outcomes, predicting probabilities with a logistic curve. Support vector machines, or SVMs, excel at finding the optimal boundary between classes. Decision trees and random forests add a layer of complexity, breaking down decisions into a tree-like structure for better accuracy. And let's not forget neural networks, which mimic the human brain to tackle complex patterns. Switching gears to unsupervised learning, we dive into a world where data is unlabeled. Clustering algorithms like k-means and discount group similar data points without any guidance. Imagine analyzing your blog visitors. These algorithms might reveal that 40% are comic book enthusiasts visiting in the evening, while 20% are sci-fi fans checking in on weekends. Hierarchical clustering can even break these groups down further, allowing for targeted content creation. Anomaly detection techniques such as one-class SVM and isolation forests help identify outliers, while visualization tools like PCA and TSNE making complex data more digestible. Lastly, association rule learning with algorithms like a priori uncovers interesting relationships in your data. Each of these algorithms plays a crucial role in extracting insights and driving decisions in a data-driven world. Visualization algorithms serve as fascinating examples of unsupervised learning. Imagine feeding these algorithms a mountain of complex, unlabeled data. What do? They distill that chaos into clear 2D or 3D representations, allowing us to visualize the underlying structure. For instance, take TSNE. This powerful tool clusters similar data points together, making it easier to spot patterns we might have missed. Now let's talk about dimensionality reduction. This technique simplifies data while preserving essential information. Picture a car's mileage and age. These features are often intertwined. A dimensionality reduction algorithm can merge them into a single feature, encapsulating the car's wear and tear. This process, known as feature extraction, helps us make sense of vast datasets, revealing insights that drive decision-making. Understanding these algorithms opens up a world of possibilities in data analysis and pattern recognition. Reducing the dimension of training data can significantly enhance the efficiency of machine learning algorithms. By applying dimensionality reduction techniques, we not only speed up processing times, but also save on disk and memory space. This can lead to improved performance in some cases. Anomaly detection is another fascinating unsupervised task. Imagine identifying unusual credit card transactions to prevent fraud or catch manufacturing defects. The algorithm learns from mostly normal instances, allowing it to flag anything that deviates from the norm. Then there's novelty detection, which focuses on spotting new instances that differ from the training set. For example, if you have a collection of dog pictures, a novelty detection algorithm should recognize new breeds without misclassifying them as anomalies. Association rule learning digs into data to uncover interesting relationships. Picture a supermarket discovering that customers who buy barbecue sauce and potato chips often purchase steak too. This insight can inform product placement strategies. Finally, semi-supervised learning bridges the gap between labeled and unlabeled data. With just a few labeled instances, algorithms can leverage the abundance of unlabeled data to improve classification. Think of photo hosting services that recognize faces in your pictures. You label just one photo per person, and the system can identify them in all your family memories. It's a powerful blend of unsupervised learning and user input that makes organizing our digital lives so much easier. Reducing the dimension of training data can significantly enhance the efficiency of machine learning algorithms. By applying dimensionality reduction techniques, we not only speed up processing times, but also save on disk and memory space. This can lead to improved performance in some cases. Anomaly detection is another fascinating unsupervised task. Imagine identifying unusual credit card transactions to prevent fraud or catch manufacturing defects. The algorithm learns from mostly normal instances, allowing it to flag anything that deviates from the norm. Then there's novelty detection, which focuses on spotting new instances that differ from the training set. For example, if you have a collection of dog pictures, a novelty detection algorithm should recognize new breeds without misclassifying them as anomalies. Association rule learning digs into data to uncover interesting relationships. Picture a supermarket discovering that customers who buy barbecue sauce and potato chips often purchase steak too. This insight can inform product placement strategies. Finally, semi-supervised learning bridges the gap between labeled and unlabeled data. With just a few labeled instances, algorithms can leverage the abundance of unlabeled data to improve classification. Think of photo hosting services that recognize faces in your pictures. You label just one photo per person, and the system can identify them in all your family memories. It's a powerful blend of unsupervised learning and user input that makes organizing our digital lives so much easier. Most semi-supervised learning algorithms blend unsupervised and supervised techniques. Take deep belief networks, for instance. They utilize restricted Boltzmann machines, which are trained sequentially in an unsupervised manner, stacking layers to build a powerful model. Once that foundation is set, we fine-tune the entire system with supervised learning to enhance accuracy. Now let's shift gears to reinforcement learning, a whole different paradigm. Here, the agent interacts with its environment, making decisions and receiving rewards or penalties based on its actions. It's all about discovering the best strategy or policy to maximize rewards over time. Imagine a robot learning to walk, or veedmind's AlphaGo, which famously defeated a world champion at Go. It analyzed millions of games and refined its strategy by playing against itself, applying its learned policy in high-stakes matches. This dynamic interplay of exploration and exploitation is what makes reinforcement learning so fascinating and powerful. Batch learning is like preparing a feast. You gather all your ingredients, cook everything at once, and serve it up. But what happens when a new recipe comes along? You have to start from scratch, retrain your entire system, and that can take ages and drain resources. Imagine waiting hours just to update your spam filter. Now, online learning flips the script. It's more like a food truck, adapting to customer orders on the fly. You feed the system data incrementally, allowing it to learn and adapt in real time. Each bite-sized update is quick and efficient, making it perfect for rapidly changing environments like stock prices or user preferences. With online learning, you don't need to haul around massive datasets or spend hours retraining. It's agile, resource-friendly, and ideal for devices with limited capabilities. In the world of machine learning, being able to learn incrementally is not just a luxury, it's a necessity for staying relevant and responsive. Online learning is a game changer for systems that need to adapt to a constant flow of data like stock prices. Imagine a system that learns on the fly, discarding old data to save space while staying sharp and relevant. This is especially crucial when resources are limited. With online learning, we can tackle massive datasets that wouldn't fit into a single machine's memory.
It's like a chef preparing a feast, taking one ingredient at a time, cooking, and then moving on to the next.
But here's the catch. The learning rate is key. A high learning rate means quick adaptation, but risk forgetting important patterns, like a spam filter that only catches the latest tricks. On the flip side, a low learning rate provides stability, but can slow down learning. However, we must tread carefully. Feeding bad data into the system can lead to a decline in performance, and if it's a live system, your users will notice. That's why monitoring is essential. If performance dips, we need to be ready to hit the brakes, revert to a stable state, and even implement anomaly detection to catch those outliers before they wreak havoc. Online learning is powerful, but it demands vigilance to truly harness its potential. When we think about how machines learn, we can break it down into two main approaches: instance-based learning, and model-based learning. Imagine a spam filter that simply memorizes every spam email it encounters. This is instance-based learning at its core. It flags emails that are identical to known spam, but it can be smarter. By measuring similarity, like counting common words, it can also catch emails that are similar but not identical. This method relies heavily on the data it has seen before, using a similarity measure to generalize to new instances. Picture a new email that shares many words with a known spam email. The system recognizes the pattern and flags it as spam. This approach is intuitive and straightforward, but it can struggle with new, unseen examples. It's a fascinating dance between memory and similarity, showcasing how machines can learn from their past experiences to make predictions about the future. Model-based learning is a fascinating approach to understanding data. Imagine wanting to know if money makes people happy. You gather data on GDP per capita and life satisfaction from various countries. By plotting this data, you notice a trend. As GDP increases, so does life satisfaction. This observation leads you to create a linear model to predict happiness based on GDP. The model is defined by two parameters, theta 0 and theta 1, which you adjust to fit the data as closely as possible. Using a cost function, you train your model to minimize the distance between its predictions and the actual data points. Once trained, you can make predictions like estimating the life satisfaction of Cypriots based on their GDP. But what if you use an instance-based learning algorithm instead? You'd find that Slovenia has a similar GDP, and you could predict Cyprus's happiness based on that. This highlights the power of different learning approaches. Ultimately, whether you choose model-based or instance-based learning, the goal remains the same: to extract insights from data and make informed predictions. In the world of machine learning, preparing data is crucial. Take the OECD data on life satisfaction and GDP per capita, for instance. By analyzing this data, we can create a model to predict life satisfaction based on economic factors. Using linear regression, we find that Cyprus, with a GDP per capita of $22,587, has a predicted life satisfaction of about 5.96. But what if we switch to k-nearest neighbors regression? By looking at Slovenia, Portugal, and Spain, countries with similar GDPs, we can average their life satisfaction scores to get a more nuanced prediction of 5.77 for Cyprus. This highlights the importance of choosing the right model. Whether it's linear regression or k-nearest neighbors, the goal remains the same: to make accurate predictions based on data. And remember, if your predictions aren't hitting the mark, consider enhancing your dataset or exploring more complex models. The journey of machine learning is all about refining our approach to uncover deeper insights. The linear model we've developed fits our training data perfectly, allowing us to make informed predictions. For instance, when we look at Cyprus, we find its GDP per capita is $22,587. By applying our model, we predict a life satisfaction score of approximately 5.96. This is a powerful demonstration of how data can guide our understanding of happiness across nations. But what if we took a different approach? Using k-nearest neighbors regression, we could look at Slovenia, which has a similar GDP per capita of $20,732 and a life satisfaction score of 5.7. By averaging the scores of Slovenia, Portugal, and Spain, we arrive at a prediction of 5.77, remarkably close to our linear model's output. This flexibility in modeling shows the importance of choosing the right algorithm for our data. Whether we stick with linear regression or explore instance-based learning, the key is to continuously refine our approach, perhaps by incorporating additional factors like health or employment rates. The journey of data analysis is all about finding the best fit for the insights we seek. In the world of machine learning, the journey begins with data. You analyze it, select a model, and train it to minimize a cost function. This is where the magic happens. Your model learns to make predictions on new cases, a process known as inference. But beware, challenges lurk in the shadows. One major hurdle is insufficient training data. Unlike a toddler who can learn what an apple is with just a few examples, machine learning algorithms often require thousands, if not millions, of examples to perform well. The famous paper by Banco and Brill highlights this. Different algorithms can yield similar results if they have enough data. This notion was echoed by Peter Norvig, emphasizing that data often trumps algorithm complexity. Yet small datasets are still prevalent, and acquiring more data isn't always feasible. So while the allure of data is strong, we must not overlook the importance of refining our algorithms. Balancing these elements is key to unlocking the full potential of machine learning. Non-representative training data can lead to flawed models that fail to generalize well. Imagine training a linear model on a dataset missing key countries. The result? A model that misrepresents reality, suggesting that wealth guarantees happiness, when in fact, many poorer nations report higher happiness levels. This highlights the importance of a representative training set. Sampling bias can sneak in unnoticed, like in the 1936 U.S. election when the Literary Digest poll predicted Landon's victory based on a biased sample of wealthier voters. Or consider building a funk music video recognition system by simply searching YouTube. You might end up with a skewed selection, favoring popular artists or regional styles that don't represent the genre as a whole. And let's not forget about data quality. Outliers and noise can obscure the patterns we need to detect. Cleaning your data isn't just a chore, it's essential. Whether discarding outliers or filling in missing values, investing time in data quality can make all the difference in your model's performance. Irrelevant features in machine learning can lead to disastrous outcomes. Imagine feeding a model with noisy data or unnecessary attributes. It's like trying to find a needle in a haystack. But the haystack is full of junk. This is where feature engineering comes into play. We need to select the most relevant features, extract useful ones, and sometimes even create new ones to ensure our model learns effectively. But there's a catch: overfitting. Picture this: a model that performs flawlessly on training data but fails miserably in real-world scenarios. It's like assuming all taxi drivers in a foreign country are thieves based on one bad experience. Complex models can pick up on noise instead of genuine patterns, leading to misguided conclusions. To combat this, we can simplify our models, gather more data, or reduce noise. Regularization is key here. By constraining our model, we strike a balance between fitting the data and maintaining simplicity. The goal? A model that generalizes well, avoiding the pitfalls of overfitting while still capturing the essence of the data. It's fascinating how we handle data in machine learning. Typically, we allocate 80% for training and 20% for testing. But with massive datasets like 10 million instances, even 1% can give us a robust test set of 100,000 instances. Now, when choosing between models, say a linear versus a polynomial one, we might find the linear model performs better. But what if we want to add regularization to prevent overfitting? We could test 100 different hyperparameter values, find one that seems perfect with a 5% error, only to launch it and see it perform at 15%. Why? Because we overfitted to the test set. To avoid this pitfall, we use holdout validation, creating a separate validation set to evaluate models. We train on the full training set minus this validation set, selecting the best performer. After that, we retrain our chosen model on the entire training set before testing it. But there's a balance. A validation set too small can lead to poor model selection, while one too large reduces our training data. The solution? Repeated cross-validation. By using multiple small validation sets, we can average the results and make a more informed decision, ensuring our final model is truly ready for the real world. Evaluating a model's performance can be tricky, especially when training data doesn't match what you'll see in the real world. Take, for instance, a mobile app designed to identify flower species from photos. You might have millions of web-sourced images, but they won't reflect the actual pictures users would take. This mismatch can lead to disappointing validation results. To tackle this, it's crucial to create a validation set that truly represents your target data. A smart approach is to set aside some training images as a train dev set. After training, if the model performs well on this set but poorly on the validation set, you know the issue lies with data mismatch, not overfitting. On the flip side, if it struggles on the train dev set, overfitting is the culprit. In that case, simplifying the model, gathering more training data, or cleaning up your dataset can help. Ultimately, ensuring your model is trained on data that mirrors real-world usage is key to achieving accurate and reliable performance.